Yesterday we saw the Vinogradov's proof of the 3' problem. And then I mentioned the 2' problem. And it's a much more difficult problem. But sometimes we can make some links. And I want to show you today one of those links with the Ziegel zeros that you have seen. So for that, I want to prove something which is called the repulsion formula. A repulsion formula, it says that a repulsion property, let's say, a repulsion property repulsion is the opposite of attraction. So what when there's attraction, something exists, and then because this thing exists, something else comes there. When there's repulsion, something exists, and because it exists, the others go away. Yeah. So this repulsion property is for the zeros. Yeah. So if there is a zero, so this in the philosophy is that a possible zero would force all other zeros away from all L functions possible zero or a possible zero with a certain modulus of the same modulus all other zeros of all L functions of the same modulus away from the real axis. So all other zeros may be real, may not be real. Okay, but if you have an exceptional zero, then you can be assured of a distance between the real axis and any zero that might exist. So that's more profound than it sounds, because we want to, you remember that we did results like Ziegel's theorem and so on. So you have your real axis, and then you want to see how close you can get with your zeros. So if you can bound these, then sometimes what can happen is you can get a contradiction that I've come, I have violated some theorem, yeah, and therefore this cannot be true. So these all other zeros, these can be real or complex. Okay. And the aim of the first part is to quantify this statement. So this is known as the, this was originally done long time ago, but I want to give you a more recent proof. Recent means this is a proof of 1987 or 88 or something like that, whereas the others are at least 50 years older. And it is in this version that we will use it for the Goldbach. Okay. Yeah. Well, maybe I'm saying I'm saying more than I mean. It's not that I will use it for the Goldbach. it is this version of the repulsion property which will give a relationship of the Goldbach problem with the with the Ziegel zeros. Okay, so so we will find a condition when the Ziegel zeros condition on the binary Goldbach problem, which will make the zeros disappear. Okay, the zero, the exceptional zeros disappear. So, of course, by now you guess that this condition is not something we know how to find. Because if we did, then we would already know that the Ziegel zero does not exist. So it's going to be a conditional result, that if a certain condition, which is called the Hardy-Littlewood condition, if this condition is true, then the Ziegel zeros do not exist. This is the aim. So before that, I want to prove the repulsion property. Okay, so this is a theorem by Bombieri, and so I will prove this theorem, which is due to Bombieri. Okay, so this says that first of all, so this estimates two things. We have property one. I have n alpha t chi. This is over chi, and the sum is over some q. Okay, which is bounded by a certain capital T, and q is modulo q. This is less than or less than T C3 1 minus alpha. And I will just now tell you what these things mean. This happens if, in general, and two, if there exists an exceptional zero which we will call beta 1, like yesterday and the other days, then this sum n alpha t chi is less than sigma 1 log t t c3 1 minus alpha. Now, I have to tell you what this is chi mod q, and this is q, which is bounded by t. So I have to tell you what these things are. Okay, so the notation is that n alpha t chi, that we have seen earlier. Okay, these are the zeros. So so I would just like to recall, I've used the C3 here, so you can imagine that there should be a C1 and a C2 before. I would like to remind you that these are the things that we will use in the proof. So, so if there's a C3, then there should be a C1. There exists, you have seen this, but we will repeat it. There exists a constant C1, which is positive, with positive such that L S chi is 0 with sigma greater than or equal to 1 minus C1 by log T. T is less than some capital T, that's what is happening there, but it is greater than 2. So, which means that beta 1 is greater than equal to 1 minus, that's my C1 by log T, which is the same thing as saying that 1 minus beta 1 is less than C1 of log T. All right, this is Landau page. Okay. You recall this, then second thing is that, so you need a C2, yeah? You have a C1 and then there's a C2. So for a constant positive C2, 1 minus beta 1 is greater than equal to C2 T to the power half log T, and where C1 and C2 are both effective and computable constants. Are effective, and we can calculate them. So now I will let delta 1 to be equal to 1 minus beta 1, and then last thing that I should say is n, these are the notations. What is this n? N alpha T and chi. This is the number of complex zeros in which are complex zeros where sigma is between alpha and 1, little t is bounded by capital T, and this S is not exceptional. These are non-exceptional zeros. Yeah. So anything else that has not been explained? Yeah, the star. The star means the sum over primitive characters. So this is Barbieri's theorem. Okay. So the proof I follow is from Barbieri's book. This is 1987. The book is in French, so you have to if you want to read it, you have to be a little, it will take a little time maybe, but yeah. So it's an asterisk blue book, which yeah, it's written in a somewhat old-fashioned style, typed. You know, it's not. It's on a. It's on a written on a typewriter. So you should have a look at it. So the proof that I follow is from that book. Okay. So the reason, as I said, why I used this version of the repulsion property, because it is this version. It is there are older versions. There is Linux version. There is there is the Heilbronn version and other versions, but older ones. But I use this one because I want to show you, at least give you an idea of how it can be used. And another reason is that from this theorem, the Ziegel's theorem becomes completely clear straight away. You don't need any additional work. For free, you get the Ziegel's theorem. Yeah. So yeah. So let me start. So these are things I will need. So that's C1, that's C2. What else do I need? So this proof, the proof will require some lemmas. Okay. Have you ever seen a theorem that does not require some lemmas? It always requires some lemmas, because, well, maybe Pythagoras doesn't require any lemmas. So we require a few lemmas, and I will not prove all of them. I will prove most of them. So the proof of this theorem requires a few lemmas. Okay, so I will at least state them all. So the first one is Turan's lemma, lemma 1. This is due to Turan. Okay. This lemma I will not prove. I will not prove it because it's a very, very long proof, and it's a special case of a very long proof. So I will not prove it. Yeah. You can, if you when you have the time, you should look up a proof. So I take some complex numbers, Z1 to Zn, and these are complex, and I take some capital K, which is a positive integer. All right. Then I claim that, I claim that Turan claims there exists a little k. Okay. This little k is between capital K and capital 2k. Okay. So you choose your big K, you get a little k between capital this, such that if you take the kth power of each of these and sum them up, so Z1k plus Z2k plus Znk, then this can be bounded by Z1 power to the power of 50. How he gets this 50, I think is just for fun. To write something nice. And the numbers used in this proof are all very nice numbers: 50, 100, 400, etc. It's not that it has to be 50. Okay, it's something like that. What I mean is, this is not a precise 50. All right, it's something that will work. So there will be no proof of this today. Okay. Then I will give you the density lemma, which we will prove. Bombieri doesn't prove it either in his book. So you'll probably have to find it somewhere else. maybe collected works of Turan or something like that. And then maybe it's written in Hungarian, I don't know. So I don't know really. I mean, I haven't seen a proof. Okay. Okay. So theorem, this is lemma 2. It's called the density lemma. Okay. So this we will prove. All right. So I will take an L function. Okay. Modulo Q. And this Q, the modulus, is bounded by T. Okay. And we will let W is equal to 1 plus IV, and V is also bounded by T. Okay, but V is at least 2 if you have the case that chi is chi0. Okay. Then L of S chi has at most, which means R log T zeros in a circle you have an S here and you have a W here. So S minus W, which is less than or equal to R, uniformly for R between 1/4 and 1 by log T. Okay, so what does this mean? It means that if you have a, a circle here, so say one is here, and then you have some circle here. So this one has radius, this circle has radius R. Okay, the circle has radius R, which is greater than or equal to, 1 by log T. All right, and the zeros are inside this. So there are some zeros here. Are there? And there is a W which is equal to, so which follows the, so S is equal to W plus R, which means S is equal to W plus R. Okay, that's what this means. So we will use, what are we going to use? We are going to use L prime by L. Okay. Do you have any questions? Okay. So if S minus W is here, S minus W If it is less than half, then what do we have? Proof. Proof of lemma 2. Okay. So if S, so in S minus, in this region, S minus 1 less than equal to half, what do we have? We know that L prime by L of S chi, this is bounded, this can be bounded by rho minus sigma less than equal to 1 upon S minus rho plus big O of log of t. Okay. So now I can pull that out, this one, okay, which I do. If I take the sum, rho minus W, which is less than or equal to 1. So 1 upon, now I write this as S is equal to omega plus R. So omega plus R minus rho. This is equal to big O of log T. And then I replace this by its definition. So minus, so this is lambda n. You remember the definition? Lambda von Mongold, lambda n, chi of n to the power 1 plus r plus I times v. This is my v, yeah? This one, and I have this one. Okay. So, this is, let me keep the O of log t. All right. And then what can I do to this one? Can you find a bound for this? Does this can you use a bound? Can you suggest a bound for this? So you know that I can take this to be big O of 1 by R. Why? Because zeta of 1 plus R. Yeah, why? Because zeta of 1 plus R can be bounded by what? Yeah. So 1 upon 1 plus R minus 1. Yeah, that's the reason. So I can bound this by O of 1 by R. Okay. That's the reason. Okay. So you have what do I know? I know that if I take the real part of this, okay, then that's going to be greater than 0. Yeah. So we have, I take real part of 1 by omega w plus r minus s. This is greater than or equal to 0. And so real part of 1 upon w plus r minus 2 minus sigma will be greater than equal to 2 of r if I have the condition that sigma rho minus omega is less than equal to r. All right? Whenever I am in the circle, rho minus omega less than equal to r, then this is okay. So, so if I take the number of zeros in this, in s minus omega, so number of zeros in s minus omega, which is less than equal to r, yeah, equal to say n1, okay. Number of zeros be equal to n, then n1 is less n1, then you have the 2r here, so you normalize by the 2r. This is going to be less than equal to log of t plus 1 by r. Okay, and that's what we wanted to show. Okay. Now I'll give a name for this L prime by L S of chi for some special case when there are no exceptional zeros. So that is, I can allow an exceptional zero, but I will not allow anything else. Okay, so let's prove some small lemma for that. So I will call it fs of chi. Let f s of chi this be equal to L prime S by L S chi. Remember this? We had that. We've just seen that, L prime by L S chi. But we will put some condition on this, otherwise there's no need to give it a name. So for all chi whose modulus is q and which is bounded, okay, and that means this depends also on t, and let this be equal to 0 if there are no exceptional zeros. And suppose there is an exceptional zero, we call it beta 1, and if there exists beta 1, which is equal to 1 minus delta 1, okay. So this is an exceptional zero. Then f of s chi is equal to this L prime by L, which is, we keep the same L prime by L, S of chi, and plus L prime by L, S plus sigma 1, yeah, the difference here, S plus sigma 1. So you notice this beta 1 being written as 1 minus delta 1, this is giving you the distance from 1, yeah. This is the sigma 1, which is giving you the distance from 1, and this is chi, okay. So let us consider this case where there is an exceptional zero. It's the more complicated case. When there isn't, it's easier. Yeah. So using a known result, this is still lemma 2. Okay. So L prime by L S of chi, you have seen this several times over. This is the sum of 1 upon S minus rho plus, this is, we will, let us consider, so let us consider the case with beta 1, case where beta 1 exists. Okay. So you have S minus rho, and then you have 1 upon S plus sigma 1 minus rho prime. Okay. So here, S minus rho minus omega is less than or equal to 1, and S minus W is less than equal to half. W is 1 plus IV, and V is less than or equal to T. These are the conditions that we had in the beginning. V is greater than or equal to 2 in case chi is chi 0. All right. And the second one, these are the zeros. And rho prime, the second sum, this one sum, two sums, so that's the second sum. The second sum with zeros, rho prime of L S chi chi 1, that's the one here, okay. And this time, rho prime minus sigma 1 minus W is less than or equal to 1. Now, supposing chi is equal to chi 0.
So it should be f of, I mean, if the function is chi, right?
Yeah.
There also should be like when the proof of lemma to continue. We are writing the left side L prime by is L prime by or should be like capital L in terms.
Ah.
Because we have
Yes, 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 yes. So supposing I have chi is equal to chi 0. So what happens if chi is chi 0? In the case where chi is chi 0, what happens? This minus 1 by S minus 1 is a pole of L S chi 0. Yeah?
should be like capital F instead of capital L, and there should be some other term, right? It is not only the sum over 0.
Yeah, that's
Like
why that is why I said that we could have L prime by L.
No.
Uh,
That would be capital F of S comma chi
oh,
instead of capital L.
yeah.
I'm saying that
Oh, yes, yes, yes. That's the one.
there
Yeah.
should be also some Vigo term, right? Like not only sum over zeros, like Vigo of log t or something.
Wait, let's get it correct. So f of s chi is L prime by, but f of s chi and L prime of s chi are the same if there are no exceptional zeros.
L prime by L is something like sum over zeros plus there is some more
Some more terms. Yeah.
like Vigo of log t maybe something.
Yeah. So I'm sorry, there should be an error term. We go off. Yeah. How bad? How crude can the error term be?
I mean, S is inside the circle with
Yeah.
center W, and W is like over 1 plus something.
Yeah.
Like log t maybe.
Yeah, should do. Yeah, I think so. You're right. Thank you. So if chi is equal to chi 0, then what happens? Then minus 1 upon s minus 1 the term, which is this term, minus 1 by s minus 1? What does it correspond to? Minus 1 by s minus 1? What is it? This corresponds to the pole. Yeah? This corresponds, then the term minus 1 by s minus 1, which corresponds to the pole of what? Which pole is it? Of whom? L S chi 0. Okay? This is what happens to this one. This gets eaten up by because of this condition. Yeah? If V is greater than equal to 2. Yeah? V is greater than equal to 2 if chi is equal to chi naught. This is the condition that we are supposing. So this is absorbed by the error term. Yes, of course, if I'm talking about an error term, then I better have an error term. Yeah. Thank you. So, yeah. But I could also have written it as L prime by L. I could still have written it by L prime by L. The F. I could have still written it. Yeah, that's right. So this is absorbed by whom? By the error term. This is my error term. In the case V is greater than equal to 2, but that's what we suppose, okay? And if chi is chi1. All right? So chi1 this is equal to chi1 square, and that's equal to chi0. So, so the pole of this time, first time you have the pole of Ls chi0, now you have the pole of Ls chi1, yeah? So that gives you L of S plus delta 1 chi1 at this place, which matters, that is 1 minus sigma 1, which is beta 1. This, what happens to it, the pole of this is compensated. What do I mean by compensated? I mean there's a cancellation by the 0, which is beta 1, of L S chi1. Yeah? Because in one case you have, see, you have minus 1. I'm looking at these terms which are 1 upon minus 1 upon S minus 1. So here you have what do I mean by what do I mean by the compensated? Yeah, this means in one case you have minus 1 by minus 1 by S minus 1, yeah, and this is 1 minus sigma 1, yeah, plus sigma 1 minus 1, and the other one is 1 upon 1 minus sigma 1 minus 1 minus sigma 1. So this one is my S, 1 minus sigma 1, yeah? And so the minus and the plus, they cancel out. All right?
This is not clear, like
Which one?
the whole sentence for chi equal to chi naught. The first term is like the 1 by S minus 1.
Corresponding to the pole of Ls chi is absorbed by the error term.
Okay, I mean, okay.
Because it enters into the error term. Okay? And if chi is equal, this is the second term, okay, chi is equal to chi1, then the pole of one pole and 1 0, they cancel each other. So what's the problem with that?
I mean, last you was replacing something like 1 by 1 minus delta 1 minus 1 minus.
What you need is a bound. You don't need a precise results.
I mean, last.
Where? This one?
1 minus delta 1 minus 1 minus delta 1. Okay, 0.
1 minus delta 1 is just beta 1, yeah?
What kind of 1 by 0 is replacing? Maybe clear.
Okay, how many lemmas are allowed per theorem? How many can we expect here? So I will do 3. Okay, I promise I will do 3. The first one I won't do. I will leave it as it's long. It's similar to, can't be same of course. It's just similar to the third one. So here is my lemma 3. Yes. Chi 1. This by which your induction takes place. Remember right in the beginning that if you didn't have things that were principal, then they would be induced by something. Okay. This chi 1. Yeah, this is the exceptional chi 1. Okay, it's the exceptional chi 1. I thought. Yeah. Yeah. Now, I told you that the bounds here are all nice. Yeah. So I'm going to take R to be something between 10 to the power minus 4 and 1 by log t. All right. So, and I will take some k, which is bigger than some, what was my last constant? C what? What was the last constant? How many C's have we used? 4 then, okay. C4 R log t, okay. Omega is 1 plus IV. V is less than equal to T. V is at least 2. If chi is, so the same sort of conditions. And chi has modulus bounded by q less than equal to T. Okay, we'll call it lemma 3 because we've called the other twos. The first two lemmas, we've called them lemmas 1 and 2. Okay. Yeah, I haven't finished stating the lemma. Nothing has happened yet. These are the conditions. Then what happens? So if the function you haven't missed much, just 2 lemmas. So